Hello everyone, good morning to our another lecture on build SLM from scratch. Today, I am going to show you how have I demonstrated and how have I made MediGPT, which is completely from scratch, using the dataset which consisted of about 50,000 medical documents altogether. And I will go through step by step so that you can understand each and every step in detail. So this is a research-based project from me, and I have used this particularly for my competitions, and you can say I also use this as a open source notebook so that everybody who are interested in using this and fine tune it further can use it. So let's get started with this today lecture. So firstly, I will go through the overview. So this is just a decoder type GPT-style transformer which is entirely built from scratch. So we have used the PyTorch implementation, and the primary goal which was behind this project was to make the model understand about medical corpus, and also it should understand the we should understand the transformer internals, which is just from first principle. So as you can see, the dataset use I have written. So one of the main dataset is used is PubMed QA, which has around 30,000 documents about medical. So this is one of the main datasets, and the other two datasets also used. So overall, it's around 1 lakh data which I have with me. But PubMed QA has a greater contribution because some of the documents like diabetes and all, which would be using to test further, are basically related with this. So these are the dataset used. Then firstly I will show you the research paper, and this is the research paper which I have published so far. And as you can see, first of all, the introduction, as I said you. So first of all, why are we building SLMs? Because SLMs are such a powerful tool, and LLMs require so much of computation power, and LLMs are basically just trained on a huge amount of data and a huge amount of parameters, trainable parameters from billions to trillions of parameters, which is not feasible in our case because we are using a normal computer, and normal computer on T4 GPU is inefficient to compute such a huge power, and it also has some runtime connection issue between after 3 hours it automatically get disconnected. So for training on free, you can't use the LLM entirely. So we need a huge amount of computation power, and for that reasons we are building an SLM because it is specific to a domain, but its knowledge, its outcome is similar to what LLMs can produce. So that's the reason. And completely building it from scratch means also that we are trying to make it understand the essence of the language with just few amount of data and few amount of parameters. So that's the main way behind this project. And we'll see later that how our SLMs have produced better results. So as you can see, this is a transformer architecture. First of all, data collection. So PubMed QA datasets, as I mentioned earlier. So we are connecting the data, we are removing, we are doing pre-processing. So I will show you the pre-processing step here. So first of all, you see I have used tick token, which introduces the byte pair encoding algorithm, which is efficient for the tokenization scheme. So we can do tokenization through word-based tokenization, character-based tokenization, and subword-based tokenization. Now, word-based tokenization means breaking the sentences based upon the words. Now the problem into this is, first of all, when you I will just show you that, and what the problem is that, suppose you have something called as learn. Okay, now some people might use learn. Okay, some people might use learn here, some people might use learning, some people might use learning here, and you can see the problem here, right? Now what is the problem here is that basically based upon these three words I have to create different vocabulary words, although the meaning is one and the same. You can say learn is the base word for all the three sentences, but because that we are using word based tokenization, it is unable to capture the semantics, and as the words go on increasing, the vocabulary size will also become huge, which will be very much inefficient for our computation. Also, there is one more problem with out of vocabulary problem. Anybody knows this out of vocabulary problem? Okay, I will explain. Out of vocabulary problem means there are some words which can be grammatically incorrect, like LAARM. Okay, this is the word. Now this is grammatically incorrect and there is no meaning as such. But the transformer will directly give this the tag of out of vocabulary, meaning that this is not present in the vocabulary. Now this seems correct, but the thing is, when you are basically using a transformer based architecture, you cannot then predict what the relation of this word with the other words are. Now, if we are using any other tokenizer, then we could have at least assumed that this is not out of vocabulary, this is something related to our words. So this is also one of the main issues in the word-based tokenization. Now, after this word-based tokenization, there is something which is called as character-based tokenization. Now, what is character-based tokenization is, assume I have a word like hunting. Okay. Now I have a word hunting, and on this hunting, I have to do character-based tokenization. Now, what this character-based tokenization will do is, character-based tokenization will take this sentence and break this word into something called as a character by character. So H will be separate, U will be separate, N will be separate, T will be separate, and so on. This is character-based tokenization. Now, this character-based tokenization has one disadvantage. Now, what is the disadvantage is, the sequence length will be 2. What is sequence length? Sequence length is the input sequence which are providing to the transformer. So this is very used, sequence length of this sentence, because you know what, if sequence length will become huge. Also, don't you think this will destroy the essence of the language? Because if I look at this H, can you predict any information based on this hunting word? No, I can't predict, because these are separated. Then you can still be use HU, but still I can't do hunting. And the context size will become too huge at one point that I will destroy the essence of my language. Okay. So there is really we cannot replicate information from characters only. So what did the researchers do? Now word-based had out of vocabulary of this destroyed the essence of the language and the sequence length issue. Now what did the researchers do was, now what they did is they used bytecode encoding for subword-based tokenization. Now what is subword-based tokenization is? They will not break this word into character. They will not break this word into anything you can call as a, what you can call it. It will not break into word, but it will break it into subword. Now look at this. This is one part, this is other part. Now, how did this break this? So there are various algorithms like I know bypair encoding. Bypair encoding, what it does is a common occurrences of the word. If they are present, it will break it down into separately. Okay, that is bypair encoding. The second algorithm which I have to introduce is word piece. Word piece will look upon the probabilities about the words that are currently will be produced in the future, and based upon that, it will break down the words into some words. So that is word piece algorithm. And the third one is sentence piece. Sentence piece introduces underscore between places so that we could consider every aspect. Means मतलब एक ही बड़ा word बनेगा, right? So then we can consider every aspect of the code. So that is what these are the three algorithms widely used in the research industry. Now what we are going to see is bytepair encoding, because bytepair encoding is one of the crucial algorithms discovery which was introduced. Common occurrences it will take, and we are using bytepair encoding also in our project. So that is what TikToken does. Transformers, to use the transformer architecture, accelerate, it's just given by Hugging Face, because we want to ensure that the radiant speed of updation becomes a little bit faster. It introduces floating point accumulation, so that it only consists 2 floating point accumulation. That is some of the key advantages of the accelerate, so that we can save the computation time. You can assume like that. And sentence piece are the algorithm which I showed you, which converts into subword. So importing libraries. So we have imported, this is for visualization. Pandas is for data frame, creation of data frame. NumPy, mathematical calculation. Now this random is used to randomly seed some of the matrices which we see further. So there are some trainable matrices in the transform architecture, and these are the other basic inputs. Now the important input I have to find out is that neural network. This is the important, because transformer architecture works behind the concept of neural network, and that is the reason we are importing neural network as well. We are using train test split, so that, and the TikToker. So now we are using CUDA device, and I was using T4 GPU. Now I'm not going to run because it takes a huge amount of time. At least this will run fast, but the next amount of task is taking too much of our time. So this is paid core data, then this is PubMed data, and then this is pre-processing type. So you could get the question answer format, and we are only importing, we are only adding it if it exists both question and answer. And then the if you look at this, they are showing total documents is 6,000 after removing all of these things, because all the documents may not include question answer altogether. So what are we doing? We are actually fetching those details so that we can provide a labeled dataset to our neural network. Also, you can give this as an unlabeled dataset. We can only give the answer so that it is trained by itself. But knowing the computation power, we are giving it a labeled dataset. Then we have text cleaning. So these all special symbols are been removed. All the hyperlinks are been removed. These are removing the email addresses, and all the hyphens, or maybe we are preserving it because we know it gives some semantic information. And then after clean text, we are visualizing what are the clean text. And you can see this is a good text altogether. And you can see this is question answer format. And as you can see here, we will just analyze the corpus data. You can see the sequence length and the frequency. So more than 500 length. So if somebody was assuming what was sequence length, this is a sequence. That is the input sequence length. So that is what it is. Then the vocabulary set. Now look at the vocabulary set. Now the has the highest vocabulary set. The is used a lot in this. And if you look at the other things, and they're off and it's a common preposition, and question answer will be already used because that is what our data sets aim is. Then we have tokenization GPT-2. Now tokenization byte pair encoding, we are using for byte pair encoding as you have written. Then subword modeling, and you can see total tokens. So there are over 12 lakh total tokens. So that is a great discovery because byte pair encoding has at least, if it was character based, then the total tokens would have been a huge amount if you can see in sequence length. But in vocabulary, so it is still 26 or maybe 128 because it only represents a character. So repetition of characters only. That's why it will be really efficient in terms of vocabulary. But obviously, it will destroy the essence of the language. So now train test validation. So we are using training data, 90% of data to be training and 10% to validate, so that validation data is using because we are not trying to preserve overfitting, any cause of overfitting in it. So that's why we are doing training validation state. And now this is the keys. So now if you look here, we collected data collection, we do tokenization. Now we go to token embedding. So what is token embedding is that now after converting to token ID, we had tokenization which converted into tokens. The tokens can be assigned a token ID due to vocabulary matrix. So it will be a corresponding token ID provided. But token embeddings is something to actually capture a semantic relationship. Now, just looking at token IDs, you cannot say that how to, if tag and dog and cat are given to you, how will you understand that dog and cat are close to each other, dog and cat? So what will you do is, you will first capture the semantic of dog in a 760 dimensional vector, which is used in GPT-2. The 760 dimensional vector will be used in GPT-2, and then the cat ka also token embedding will be created, a 760 dimensional vector, and then you calculate similarity using either dot product or either using cosine similarity, etc. So these are the key methods from which you can actually deduce something which is known as token embedding. The advantage of token embedding is that it tells you how close the two tokens are, right? So that is the key essentially in token embedding. If they are close to each other, that means that they have some strong relationship between them and vice versa. So that is the token embedding. Now you might ask me, why is this positional embedding removed once the token embedding is failed to capture the relationship? So I want to give you a small example. Like suppose a sentence is there where there are two it's present. Like the dog chased the ball but it could not catch it. So there are two it's, right? The dog chased the ball but it could not catch it. Now the first it represents dog and the second it represents the ball, right? Now when we say like this, how will the tokenizer understand whether the first it is with the dog and second it is the ball? Because both the it are same, right? With respect to token, like they both are same token, so they map to the same token ID. They will have same token ID, so they will have same token embedding. So how will we differentiate between these two it? So that is why positional embedding plays a crucial role, where there are repetition of words in the same sentence. We will use a positional embedding in such a way that the first it will map to capture to its corresponding dog, and the second it will correspond to the ball. And we capture a position such as, are you at the beginning of the sentence? We'll ask one question. So that will be first it will say no, the second will also say no. But are you at the middle of the sentence? Are you after hyphen or something like that? So that will be a key indicator that we will actually, the main reason behind this is we want to separate or repetitive words, the embedding should be different. So that is cumulated. The token embedding and position embedding are cumulated together to get the input embedding. So in the diagram it is not shown, but you should understand after positional embedding what gets passed to the transformer block. This is a transformer block. That is the input embedding. Layer normalization, why layer normalization is because while training this while backward propagation is really tough when the values are too large. There's intrinsic behavior, you can search it on YouTube. There's intrinsic property which helps us that that curves which are after every training it gets segregated very fastly. So that you cannot actually normalize. You need a normalization scheme. Also, vanishing gradient problem, the vanishing gradient problem, exploding gradient problem, that is also solved using layer normalization. So that's why using two-layer normalization in the transformer block. Multi-retention is one of the key discoveries behind the transformer block, which also computes the context vector in the this. So I will just show you the code, then I will explain you step by step. So we do batch sampling. So as you know, we cannot process all the data at once. So we convert our data input samples to batches so that we will train it in limited size of sequence. So that is what. Now this is self-attention. Now this is a part of multi-attention. What does self-attention tell it? If I am the current token in my current batch, what is my relation to the current token? So how much I should attend myself to the other tokens? That is what self-attention captures. And that shows whether the two words are strong similar or weakly similar. So I will show you attention course diagram, and I hope it is, yeah, this is now. Why is it not loading? So look at this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So understand elevation belongs to elevation. This. So look at the scores. Now this is the aspect. So whichever gets the highest score have the highest attention score. So who has the highest attention score? So you can see curvature 0.77 then NDVI. So that means that essentially means that elevation is strongly related to NDVI and so on. So higher attention score, that means you have higher value, means higher relationship between them. So I wanted an easy diagram for this so that like this, yeah. So if you see attention rate between token control life and short, and look at this, life first, high, short also high. So this means that these words are having higher contextual relationship. And what it is doing is this is masking of the attention score. Now what it is masking do is that see GPT are evolved to consider next token prediction, and if we ask it to predict the relation between the next token, that will be doing like a cheating to these tokens, because our job for this token is to just predict the relation between itself and the previous token it has discovered. So that is why we are masking this feature, doing upper triangular matrix above diagonal to 0, so that we can actually sense what all things are here below this, so that it will capture the semantic attention shift. And that is what it is. So that is. Now what is an attention mechanism? This is called as. This is called as a query and this is called as a key. So query is what is our input embedding from which you are calculating the attention score. These are the keys which are all values which we get, and the values are basically what are the values inside this all embedding. So that is what query key value concept come from. And you can take it as a terminology of a bank. Like in a bank you have a person coming to you and asking for some bank details. That is what a query to the bank officer. Now the bank officer has the right to all the lockers. So all these lockers act as a key, and the value is the value that is present inside every locker. That is the value. So this analogy can easily understand about the serial attention. So that is all. So you can see batch size, then sequence fit, and the context fit. These are all the things. Now you can see here what is this done is this is Q into K transport, which is the formula. And then you will say that what is this done. Now this is just doing proper scaling of the head, because we are doing this with respect to head size. So that is what is done. Apply the causal mask, prevent looking ahead as I explained you. Then attention weight. Attention weight is just normalizing the attention score so that people actually understand it with probabilistic term, because some value can be negative, positive. You can't tell which is more significant. So attention weights is using softmax on it, and then after using softmax, we divide it by before applying softmax, we divide it by the square root of the variance. Now the square root of the variance is because the square root of the variance helps me understand the deviation, because initially these values are randomly assigned to a key value random. So because it's randomly assigned neural network linear, so there can be variance which is up to square root of variance. So that's why we are head dimension. Sorry. So it will be square root of head dimension. So square root of head dimension will be essential to just capture, reduce it down so that we could get proper understanding so that the values don't go too large and it will be difficult for neural network to converge if it happens. Multi-attention is a filter attention say derived. So we just take multiple head perspectives and just then do multiple attention so that we could capture multiple perspectives. Like the a man painted, an artist painted the portrait of a woman with a brush. So one perspective can be a artist which has painted the portrait of the woman which is holding a brush. So a woman is holding a brush and the artist is painting it. And the second perspective is that the artist is only painting the woman, but he has a brush. So there are two perspectives, right? But how will the single attention capture because it is only single vector? So we add multiple attention so that we add multiple head dimensions and multiple head attention. So that's why we also give a hyperparameter that is the head size. So that is what is multi-head attention going on. So number of heads is the key parameter. If it is 2, then we capture 2 perspective. If it is 3, then we capture 3 attention. And what is head size formula? That is outward dimension divided by number of heads. So you should remember this. And then we feed-forward neural network. Feed-forward neural network is used to basically capture more non-linear relationship between the tokens, which we are cortex vector. See, if you look at my diagram, after getting the multi-head attention, we go to dropout. Dropout is basically just a signaling and non-signaling some of the neurons so that we can eliminate the dead neuron problem. You can search it out on YouTube because dead neuron problem is basically lazy neuron problem that some neurons do not actively contribute to my output. So that's why we are doing this dropout layer. Then we will feed forward neural network. Now after going to this context vector, we get feed forward neural network where we use the concept of expansion and contraction. So expansion is done first, capture the nonlinear relationship, then we apply some GLU activation function or ReLU activation function and leaky ReLU some of the activation function so that we could capture the sense of the language and nonlinear relation. We could capture more attention, we could capture more information based upon the underlying text, and then we again contract that so that we get the normal context vector. So there are trainable parameters because of the expansion contraction scheme, and it is recommended to use a hidden layer of size 4 into input dimension so that we could actually preserve a balance between the computational time as well as the number of attention you get. And it is experimentally proven. You can also use the higher value if you want. Then again drop it. And finally, we get a context vector here, which is then passed to final layer normalization. This is done to again normalize the value with mean equal to 0 and standard deviation equal to 1. Then we have the output layer. The output layer shows if we create a logics matrix. What is created a logics matrix? Logics matrix is created with the size of input sequence and the vocabulary size. And that will show. So I will show you the logics matrix once so that it becomes clearer to you. Logics matrix. So what does logics matrix do? That sequence length into and it will reduce. Yeah. So it is called as a confusion matrix. Look at it. I want a clearer image. Why is the main image? So logics matrix, yeah. So you can see here, this is the input sequence length, and this is so there they are showing is that the relation between any two words. This shows relation between the two words, and looking at this, you can say that in yeah, this is the key. This is what I wanted. So this is the logic. Now logic is then converted into softmax. Now this is what input sequence into vocabulary size. So even if this is we are considering for one token and it's also vocabulary size, then we apply softmax, and now we get the probability term. Because of this probability, we can understand that for the current token, which is this column, which is denoting the current token, what will be the next token which is predicted by a row, which is nothing but the vocabulary size, which is the amount of vocabulary tokens which I have in my entire grammar. So which we did in the starting between byte pair encoding, that is what we are referring here. And then you look at the highest probability, and this is just calculated as my predicted token. What is calculated? Predicted token. Now the actual token maybe this, I don't know. So then we compute the loss, which is called as binary cross entropy loss. that is summation of minus of summation y log ti, and using that we backpropagate the network again, we update the trainable parameter, and then we again go with the forward pass. Now the forward pass is just this which I have showed you here, which is a forward pass, and the backward pass will go again through these all terms and update the trainable parameters. Now where all there are trainable parameters? Trainable parameter token embedding, positional embedding, then there is under multi-head attention, lower normalization. Lower normalization has two parameters to normalize, scale and shift. So you should remember that scale and shift are two trainable parameters there. Then the layer normalization, feed forward neural network, the hidden layer, the weights that are associated with the hidden layer, output layer and the input layer, and then these all largest metrics are the trainable parameters. These all things are trainable parameters, and that you should remember. Then coming back to this thing, now we go back to our notebook because I think we have covered the essential concept. Then this is a transformer block. As I showed you, we are just assembling all the blocks one after the other. Then the MediGPT architecture, we are just using transformer block, which I think is we are using the input layer, then the transformer block, then the output layer, and that's what we have shown here. This is the input embedding, as I explained earlier. This is input embedding, right? And then we do this whole thing. I don't have any doubt here. Then we go to parameter statistics, the total number of parameters. Now this is what the trainable parameters mean. Now there are so many parameters in just one SLM. Imagine if I was building an LLM, it would have been from billions to trillions, right? So in just a SLM like this, it has over 77 million parameters. And this is add-on-W optimization, which uses momentum, like a momentum scheme. Now simple gradient descent can fluctuate or maybe cannot find the global minimum, it can find the local minimum. So that's why we're using add-on-W optimization. And gradient flipping also used in add-on-W. Then validation evaluation and checkpoint saving. Now checkpoint saving is just that we are training the model over multiple iterations and we are saving the best model, mathematical model which we fetched over the time steps. So that is what checkpoint saving means. Then warm up says this is learning rate warm up, which is just a hyperparameter, so that you could actually converge the network. And then you can see evaluation function. Now this is a training loop. Now if I view this notebook, the most of the time which will go for you is in this training loop. We are using maximum iteration, which is nearly you can fix it anyhow. I was using something like if you can see here, this was a 30,000 iteration. So 30,000 iteration, and we estimate the loss, then we append the train and validation loss, and then we print it. And if now we are here saving checkpoint after every pass. Now if you add a if condition, because I think that could be better, that if the training is better, like we are sure that the model improves, but what if the validation loss keeps on increasing, so that is overfitting, right? The training loss will definitely get lesser. I will show you the diagram below, because it is learning from training data, but the validation loss is something which actually tells you whether it is actually learning the data or learning the pattern. So they are two different things. Learning the data is bad because that is just ratta, like ratta thing. You are just memorizing the data, and that is not useful for me. I want you to learn the pattern. Okay, so if you do that, then you can be useful in any sort of data. And you can see add-on optimizer, then gradient clipping, and this is the backward path, right? Backward path. So we train. See, training loss continues to decrease, but when you look at validation loss, after one point it is slightly increasing, which is telling me that slightly it might be overfitting at some point, because now it is just trying to memorize the data. So at this point, at this evaluation step, I think that you can stop here because the validation loss is comparatively low. Although we don't know if further the validation loss goes on decreasing, because we have run to 30,000 iterations, so that's the reason. Now we, after doing this pre-training, we are using evaluation. So what are we doing? Diabetes symptoms. So we are generating some text. So look at the symptoms of diabetes include coherent approach. So you can see some of the keywords like two gesture, skin assessment, and the neural relative table. Then you can see global score, morbidity test, hospitalization, and something like that. Also, once when I had published the research paper, I will show the output when published on 30,000 iteration. And if you look at the diabetes one, if you look at this, I think you will see. Now, if you look at this, you can see blood pressure, hypertension. You can understand that actually diabetes and this has higher confidence than just hypertension. Yes, brain or heart abnormalities. So this is exactly what diabetes had. Okay, I can see still that there is some sort of noisy input, like you can see heart failure is also true cardiac conduction. And now we don't know medical sonar, but still I feel like it should actually give better. So it has understood the language, it has understood the medical concept clearly, but still, if you look at his statement, you can still say that somewhere or the other, he hasn't really given the data what a normal, unsophisticated human wants. Like, it is still a little bit confusing. Like, electric system is there, some hard words are there, hypertension, nobody knows it. Then, arrhythmia, even it is human heart rhythm. So I think this is still a good output. Then I have used this clinical symptom hypertension. So this is again correct, right? And this is not something which was present in the dataset. This is actually generated by itself, right? You can say the first one was actually generated, but look at this. This is just, it is generated by itself, and this is just great discovery, I would say, because you can say that even in 77 million parameters, it has understood so many things. Like you can say that when I trained this, I think it actually converts to legal minimum, because you can see all the tests, because ultrasonographic, this all things with the 56-year-old patient, these all things are generated by itself. This is not something which have input data. So you can see more outputs here, and that is just about. Now, what I have done yesterday was little bit less situation, so that you can see that now this is little bit not that great output, but still it's decent output. Now, validation loss and complexity loss are two metrics to actually. Now, as I said, we will binary cross entropy loss, right? So you can see this. We get the loss, we get the loss, and then we get the perplexity. The average loss is what? We calculate the cross entropy loss for each of the token in the batch, and then what we do is that in the batch, calculate the average, and then we do perplexity loss. Now, this perplexity of 2959 means that in my data of vocabulary size of maybe 72,000, I am still uncertain about 2959 token. That means I have doubt in this 2959 token. Set of the token, I am sure that they can't be that next token prediction. But for this token, I am still unsure between 2959 token. That is what perplexity loss actually means. It is calculated by exponential of the validation loss. Okay, here. So E raised to 8, which is approximately 8. Calculated, it will be around 295. Yes? So no need it. Visualization. No, this is just how cosine learning get scheduler actually, because this is hyperparameter we also don't know. We are not actually set to a simple dividend preset SGD. This is cosine learning get scheduler. So it will be a cosine curve and total frequency distribution. Now you can see here this graph and the above graph somewhat similar. And this is the medical corpus sequence length. So as you can see, the sequence length is going on increasing. Okay. So this is a box plot, right? This is a box plot which actually this is a self-attention heap. Now because there is so much tokens, you can't actually predict. But with zoom in close, you can see some blue and green dots. So that is something which is self-attention heap map. And average loss, so you can see smooth train loss and validation loss. Okay. So train loss actually decreases, validation loss increases. Okay. So medical term analysis. So this is just frequency in the generated text. You can see patient treatment deficit. So it had actually understood the medical. This graph shows that it has understood the medical influence. Clinical is less, but we know that the other words are really relatively high, which is a good thing because it has to do that. This is about the generated text. So the first graph which I showed you about was about the data set. So that's why I am showing you this graph so that you can understand what is happening. And this is just a model way distribution so that domain specific analysis. So as I showed you, it clearly demonstrates the biomedical terminology acquisition. So it has understood the biomedical terminology and it has generated clinical text and MediGPT strongly represents which is the diagnostic treatment, etc. Now, dataset challenges medical vocabulary complexity because the medical datasets which are clean enough are not open source, so that it was difficult for me to actually first get it from different sources and then just use it all together, because if there are multiple data sources and to convert it into same styling, like for that so that the neural network understands easily, it's a difficult task. So that is the medical vocabulary complexity. abbreviation for this, so that is the thing. Writing style, this is to heterogeneity, to make it homogeneous, that was difficult. And something long range dependency, like long range dependency is also really seen there. And limited compute resources, because this is an SLM, not an LLM, so you can't expect some great results at one glance. But yeah, surely the future goal can be, you can fine tune this model and give more medical context to it, so that it generates more better results, because now it is understanding medical terminology. I think just we have to do here to incorporate more data, maybe around millions of data, because after that and use some powerful machines, so that you can increase the number of iterations, so that it gets trained and use more complex or robust transformer architecture. Like this, we couldn't add skip connection here because of the computation limitation. Okay, so this is the architecture modification, like what we did the previous, like the what are the different things, these projects are very rare, but if somebody does it, so they, what we did is embedding dimensions increase, so that we capture more relation. Then gradient clipping, we didn't use SGD, simple gradient descent, we use cosine eliminated scheduling, we use Adam, we haven't listed it, Adam optimizer, we have used gradient clipping, and we have actually built everything from scratch, right? So this is we can use a RAG system, we can use flash attention. These are all the future aspects. You can look at this, and you can see here that you can see what we can demonstrate from here is that we can say that it is clinical language pattern identification, and it is medical corpora produced noticeably, because we see they haven't generated something noisy, something anything silly. Looking at this, you can tell anybody who is looking at this at a first glance, you can tell in that yes, this is not something which is irrelevant to medical. This is medical content. Inflammatory changes, then the red gene syndrome, then the experimental by subgroup analysis, opioid, then lymph node. It's all a medical terminology. Again, mitochondria. I am not too good in this, but even if non-unsophisticated, this is the other notebook which had created. This is another best notebook, because this creates a realistic, you can say, mystery stories. And I was so impressed by this output, because it actually understood the context. It actually understood how to create stories, and it is just a tool which will create stories, multiple stories. And the only thing I have to change is the maximum token length of the output, so that I could distinct the story length. But yeah, it was really great achievement at that point. So research paper, I will just go through it. I'll just show you what I have written. So you can see here the dataset size documents 15,000 data, but then we lowered it down to 6,000, because all of them were not in good form. Then you can see uh, methodology, we use data sources, then embedding dimension, attention head, transformer layers, then hidden dimension, context length, and all that thing. Model architecture, you can see attention score, softmax. This is what we do. Then the multi-head attention, again, token embedding, position embedding, all position embedding is very low. Now, can anyone tell me why is token embedding, position embedding, parameter count is low? Because the thing is what you should understand is token embedding or calculated, token embedding is calculated for the entire vocabulary, right? But the position embedding is not for the entire vocabulary, because position is only, you have to calculate the position in a particular sequence, right? So it will be just the position, like the embedding dimension into the position, like the number of element of the context vector. So that's why you can see that vocabulary size is 2 inch and the context size is 1024 in GPT-2, if I'm not wrong, and in token embedding is around 50,000. So you can see the significant difference, and that's why this is a difference of a 100 scale, because naturally our our vocabulary size and the context vector are not one and the same. So that's why the difference of 100 times is, you see, this is a corpus analysis of the generated text, and multi-attention is in different perspective calculation. That is what it is. And you can see I use optimizer Adam W. This is paper tells you everything, like what all things I have done. Now this is all the text I have generated. Look at this. Doesn't it look generated like a GPT? It is generated by my model, but look at this. Still, I can see that it is data. I'm not too sure whether it's correct or wrong, but still, I'm pretty impressed by its generation of text at this time, because this is just crazy. And look at this. Now, MMHG no space, but still, you can still it has understood the essence of the language. And this is when I train it for 70,000 iteration, right? So as you increase the number of iteration, then you get better results. And 800 GPU is relatively $10 per month, so that give better results accurately. Then these are all the evaluation parameters. How are we doing evaluation? See, to evaluate a model, what I did was I just pasted this output to an external LLM which is trained on millions of and billions of parameters, right? Billions to trillions of parameters. This LLM has got the essence of the language, it has got the essence of the medical terminology. And when I pasted this output, I said over 10 LLM models and tell it to rate it from 1 to 10. After this rating is completed, I took an average and just pasted it here. And I have kept it as a proof so that if somebody asks me, so I have the proof ready. So these are all the things. And obviously, AI can hallucinate too. So the future scope for this is I'm also using the evaluation metrics from human, especially doctors, so that they could guide me better because these LLMs are trained basically on the external data, right? So you can't say whether predictions are accurate or not. So that is a thing you should do human-based evaluation as well. This is evaluation done purely with an LLM so that I can minimize the cost of evaluation as well. Medical accuracy is relatively low because I said earlier, whenever I generated some text, sometimes you can see that some sentence mismatch, or maybe you can't say whether the numbers are relatively correct or not. So that is what how will improvements with more resources. So this is all the things. So acknowledgement to Hugging Face dataset, then PyTorch community for the deep learning framework, and TikToker faction tokenization, and course instruction from Vijay for the guidance. So that's it from my side. I think this is the overview, and I have showed you today about the MediGPT research paper. Now tomorrow, I will show you about the Dungeon Master GPT research paper, which is another project which I have created as an SLM. So that's it from my side. Thank you so much.